Good afternoon, everybody. My name is Sorja Petran, and together with Kurt Emil Eriksen from Velux, I will moderate the sessions in the buildings panel number 8. So, welcome to the first session of this panel, Buildings, Technology and Systems Beyond Energy Efficiency. We will have 3 presentations today. And the panel topic will be on how to combine building energy demand and energy supply systems to reduce CO2 emissions. I would like to present, first of all, the speakers. We will have first Heidi Nordstrom from Halmstad University, assistant professor at the School of Business, Innovation and Sustainability. Then we will have Luis Neves from the Institute of Systems and Engineering and Computers, INES, at Coimbra, professor at the School of Technology and Management of the Polytechnic of Leiria. And then we will have Suran Chatterjee from Central European University, postdoctoral researcher at the university, and doing research work in environmental economics and energy economics. First of all, we have 3 presentations today. So we will have maybe more time than usual for the questions and answers. So with during the presentations and after the presentation, I will invite you to write the questions that you want to pose to the speakers in the question and answer sections in Whova. Yes, we will try to answer in the 5 to up to 10 minutes question and answers after each presentation. The presentations will be recorded, but we have all the speakers in here in order to answer your questions. So before inviting the first speaker to give the first presentation, I will introduce Kurt Emil from Velux, just to say a few words, if you want to add anything, Kurt.
Yeah, I'm very happy with the introduction you made. I think you did it tremendously good. Thank you for that. My name is Kurt Emil Eriksen. I'm working in Velux, and I have had the pleasure to be at eceee quite some times now. I'm so disappointed that we could not meet in person. I have really looked forward to it. But I can promise you that we will have a very good session here, which are going to take place now, because there are some interesting presentations on how buildings can bring us to carbon neutrality. And with those words, I think I will give it back to you, Orion, and to share the session, or to manage the session.
Thank you, Kurt. I will kindly invite Heidi, the first speaker, to give us a presentation on Vanguard with the new GDH technology. I will not say anything about this. Please, the floor is yours, Heidi.
Hi, I am Heidi, and I'm a manager for a research project, Ranagård, with the new 4th generation district heating technology, together with Malmö University and funded by the Swedish Energy Agency. I will start with background. Heat Roadmap Europe 2021 is an EU project which Halmstad University has been part of. It's about mapping where excess heat are wasted in Europe, which is extremely important because it can be used to diminish the new generation of heat. There is enough excess heat for heating all housing and premises throughout Europe, according to Mattison. The EU has set aside millions of euros for district heating projects. The level of district heating in Europe is only 12%, and it will increase up to 50%. Unlike Sweden, where we have 58% today of heating and hot water use in housing and premises supplied by district heating. The obvious choice is to use already generated heat instead of generating new heat with expensive technical solutions. We are going to have more near zero energy buildings with the new renovation wave carried through in Europe when following EU directives, which implies that the new fourth generation of district heating with low temperature should be sufficient for heating twice as many buildings and premises, especially as all new buildings will be constructed for near zero energy demands. So the local company HEM is expanding their district heating system for 550 new flats in Ranagård, which is situated in Halmstad in the south of Sweden. HEM, Halmstad Environmental and Energy is testing a new fourth generation district heating technology developed at Halmstad University by some colleagues of mine. The university follows the technical work in one part of the project for quality assurance, and our university, together with Malmö University, is also making a study on the acceptance of new technologies. So, area 1 of the 3 planned areas, the figure is showing the buildings and the 3-pipe district heating grid that will be developed at the site Ranagård, where HEM is expanding. So heat demand for 550 new flats in Ranagård. One can see in this table that 4,500 or more megawatt hours for heating and hot water are needed in total for the 3 planned areas. So we got the heat demand in Ranagård with input from R3 Engineering. So how did we get here? The first generation of district heating were established already in 1880s, supplying steam in concrete pipes. And the technique is still used in both New York and in Paris. Second generation started in Germany in 1920s, based on supplying hot water instead, but still 100 degrees Celsius. And it was known as the best technique during the period between 1930 and 1970. The third generation of district heating was invented by engineers, still had high supply temperatures, 80 to 95 degrees Celsius, and hot water, of course, but there were prefabricated pipes and pre-insulated pipes for supply and return of the hot water. Altogether, it made it more efficient, and it was considered as the best available technique, BAT, from the 1980s and on. Finally, the fourth generation of district heating was tested in Denmark in the 1990s for distributing solar heat. Its main characteristic is significantly lower supply temperatures, below 70 degrees Celsius, resulting in lower heat losses, and the possibility to use district heating with plastic pipes instead of expensive steel pipes. Low temperature district heating using 2 pipes, supply and return, in one casing in the distribution grid has been tested in both Germany, Sweden and Denmark, and it's now often considered the best available technique. One alternative fourth generation district heating is using 3 pipes, where the third is for supplying water circulation without any temperature contamination of the true return temperature to site of a Falk and Werner. The project's technical parts are followed separately by Helge Averfalk at our university. This is his illustration. The new technique is based on proven materials and methods, but they are used in a new way, in a new combination, so to speak. I'm not an engineer, as Averfalk, but I guess you all are familiar with the hot water circulation needed in all buildings connected to district heating or other heating forms. In a single family house and multi-family houses as well, this circulation is placed within the building's system boundaries, as one can see in the first two illustrations. The new is to add a third pipe for circulating the heated supply water without losing any heat to the return pipe. The demanded temperature can be lowered quite much, as one can see in the marked figure. Return 20 to 25, supply 50 to 55. NTU, you have at the radiator symbols, is the unit of thermal number of thermal units, which of course increases with a new technology. So it might advantageously consist of floor heating, providing a larger area for distributing the heat. And that's all I'm going to say about the new technology, as I'm not an engineer. My part as a project manager is carried through together with Christian Ståhl at Malmö University, and it's about mapping the acceptance and usefulness of new technologies. An important motive for implementation of new technical solutions is the various actors' perspective. This is not a comparative study of any kind. We just want to identify and try to understand the basis for the actors' decision-making that are related to new technology. We focus on energy and district heating solutions such as for GDH, but our ambition is much broader. We want to explore facts and thoughts about major decisions on new technology, and therefore we also look into organizational issues. So the aim and objective of the study is to look for possible answers to the following questions. What opportunities and holdbacks lies in the development of new technologies, especially for GDH with the three-pipe solution? And are developers really ready for new systems? And what impacting decisions are taken and which ones are actually needed? So are new methods and strategies needed for introduction of new technologies and solutions? That's the ultimate question. The chosen groups for our interviews are planners and property managers within construction and within the energy sector, and of course manufacturers and suppliers of system components. The more interviews we make, the clearer the results, and we want to do as many interviews as you can during the project. So, which points of departure do the company's perspectives have? Economic, technical perspectives, sustainability, ethical perspectives, or perspectives of corporate culture, or our perspectives? We didn't know what would occur and which ones were most important. Well, the economic and technical perspectives, together with sustainability, were equally important. But maybe first and foremost, the corporate culture in the companies were the most important ones. This was especially obvious in the bigger municipality companies, often with politically chosen boards making plans and strategies. So, although we are not quite finished with our analysis, these are some of the tracks we could find actually. So, they're not finished analysis. actually made us nevertheless see that some sentences in our texts from the interviews were recurring several times. And that was, for example, the long-term perspective impact for buildings, as well as district heating, 80 to 100 or more years, making all decisions on investments exposed to long and, of course, needed discussions. But that is acting as a holdback for new investments, new technologies for testing. The awareness of CO2-free district heating as an important part of fossil-free future is, of course, a smart possibility. All were aware of that. And furthermore, all companies have policies and or action plans for this future, and district heating is included in the plans. So our ultimate question asked was, are new methods and strategies needed for introduction of new technologies and solutions? That was the question we wanted to answer, and the work continues. So far, we have had very good contacts with construction and managing companies and energy companies, and will go on contacting manufacturers and suppliers. So finally, if you have any questions or want to have contact, send an email to me, to heidi.nordstrom@hh.se. So thank you for your time.
Thank you very much, Heidi, for this insightful presentation. And yeah, we have a comment on chat. I didn't identify any questions. In the Whova chat, but I would like to ask you a question about what do you think, is this fourth generation district heating technology possible also for the retrofit of existing networks? I mean, when we have some buildings, so new buildings or buildings retrofit at the NZEB level, but only few buildings from the district, what do you think, if it's possible, and what would be the challenges for that?
Of course, it's a question, it's an alternative for new buildings, for new districts. Absolutely. And sometimes, if they are really old district heating systems, they have to be changed, or they have to have new pipes and so on. And in that case, of course, it's an alternative. But if you have like district heating built for 20 years ago, you don't have to exchange the pipes in the nearest future, of course. So.
Yeah, thank you.
I would like to raise a question as well. I think it is a very interesting presentation you have given. My question would go in a direction about what is the optimum, or can you explain the optimum between energy demand in the building and the district heating system? I mean, moving towards passive houses would probably not work in an area where you at the same time invest in district heating. So do you have any optimum where you would say, if we want to use fourth generation district heating, we should be at this and this level in the energy performance of the buildings?
I think that absolute optimum would be passive houses, or even more energy efficient houses with, of course, ventilation with supply and exhaust air with recovery. But you still have to have hot water for your tap water and so on, and you still have to have some heating in some way. And if you are using this low temperature district heating, it will be very suitable for that purpose, to to cover the heat demand, the very low heat demand. You don't have to have a high temperature district heating to cover that. So I think it's a very good match, because when you have the low temperature district heating, you have you can manage twice as much or triple as much heat demand in a new district, for example. So that would be, yeah, a perfect match. So.
Okay. I would be challenged by the investment then, because if we are using that small amount of energy in the building, isn't it cheaper just to install a heat pump?
Well, I think that the best energy is the energy that we actually don't need, and to use the energy that we actually have. And in Sweden, the district heating is mostly biomass, but it's also waste, of course. And our waste is decreasing gradually because we are sorting out things for reuse and recycling and so on. But there will always be some things that we have to incinerate. So there will always be some district heating. And another positive thing is that just as like in a house, if you have a waterborne distribution system for heating in a house, in a building, then you can actually, you have your choice on how you want to heat that water. And it's exactly the same back in the district heating system out in the street, under the street. So I think it's just the best solution we can have, because we had a meeting last week with the municipal housing company in Halmstad, and they had some explanation to why they don't want to use the fourth generation district heating with one unit for exchange unit for each flat. And I mean, the government in Sweden, they are giving some grants, 75% grants, if a housing company building new houses can lower the energy need 2/3 to just have 1/3 of what's required in the building regulation. But there are different ways, several ways of reaching that goal. And one of them is to have passive house, or better, near zero building with 90% efficiency supplying and exhaust air with recovery. And then you will need just a small amount of heating, and you can come down to this 1/3 that will give you 75% grants of the investment. But I mean, engineers are engineers. I may be sticking out my chin here, but they want technology. So what the first house that will be built in Ronnegård will have heat pump, and then it will have solar PV to generate the electricity for running the heat pump. And in that way, it will come down to the 1/3 of heat demand. But I mean, if they had built the insulated and air tightened the envelope of the house from the beginning, if they have thinking that way instead, they wouldn't have no need for the heat pumps or PV or anything. So I mean, the simplest solutions are often the best. Yeah.
Thanks very much for your answers.
And the questions are coming in. We have a comment which match with the previous explanations very well. It says, I do see some appetite from this technology in Flanders, Belgium, and all connected houses are very well insulated to passive house standard, confirming it's a good match. And question, was the acceptance measured only among industry members of boards, or was it also tested among citizens?
Sorry, I couldn't actually hear the last, what you said.
If the acceptance was measured also among citizens, not only on the industry member boards.
All contacts we have had in the project is with different companies in construction and energy and so on. Or I didn't recall your questions quite right, maybe.
Was the acceptance measured also among citizens?
The acceptance method, no.
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 Okay.
Short answer.
Yeah. We have another question from Louise, but I will ask Louise to put in live, if it's possible. Not let me read it.
Okay, thank you. It was just a curiosity to know if there is an idea of the order of magnitude of the infrastructure costs of the fourth generation distributed heating versus the previous generation. So is there an increase in costs associated with this change in technology, or is just a matter of a different type of installation?
Of course, a third pipe means increased costs, of course. And if you have plastic pipes, you can have 3 pipes in one casing. So it could be quite not cheap, but not more expensive than other stuff. But if you have an area or district where you have to have some low temperature and some high temperature, then you have to have the steel casing. And that's the problem with the welding if you have 3 pipes to get to the pipes, so to say, to weld. So then you have your traditional 2 pipes, steel pipes in one casing and one separate casing with 1 pipe. Okay. For the third pipe, so to say. And that will, of course, be a little bit more costly.
But there's at least an expected significant difference in terms of losses, for instance, in terms of the quantity of energy lost. So that would a little bit, but essentially for the operation, not for the builders, right? So for the builders, it's an added cost, so it explains a little bit the not so good acceptance, perhaps.
I mean, in all investments, they are based on what you are gaining in the long term.
Yeah.
So with that view, with that perspective, it will not be any more costly than other solutions, actually, because as I've written in the article also, it's 80 or 100 or more years, that perspective that we have for these systems and for buildings. Mm-hmm. So, I mean, if you have a heat pump, you have to do something with it within 10, 20 or 25 years. And that will be continuous costs in the running.
Okay, thank you.
Well, thank you, Heidi, for the discussion and for the answers. And I will invite Luis Neves for the next presentation. That will be on scheduling supply and demand for optimized and cost-effective energy use.
Good morning. My name is Luis Neves, and I'm here to present a work regarding the optimization of the scheduling of a battery and appliances in order to participate in a demand response scheme. The work was developed by Lucas Ampighi as his master thesis in electrical engineering under my supervision at the Polytechnic of Leiria, Portugal. The motivation for this work is due to the current energy transition towards a fully renewable and based power system, which brings additional source of instability by the variation in the energy resources like wind, sun, and rain. Demand flexibility has been pointed as one of the possible solutions to these new problems, but a significant part of the consumption is due to millions of small residential customers, which have limited ability to offer significant load changes, even if we forget the issues associated to their dispersion. However, the use of energy storage systems, namely through small dedicated batteries, combined with load management and eventually small self-generation, may provide a possible useful role for this type of customers. So the objective of Luca's work was to implement a control algorithm to decide upon the charging and discharging of the battery and the scheduling of appliances with a minimum discomfort to the user. The concept of demand response is well known. The objective is to stimulate consumers to adapt their consumption to the needs of the grid management in a way that minimizes the need for excessive and expensive idle capacity, so helping to keep the balance between a now variable supply and the naturally variable demand. We focus on the price-based demand response, assuming a real-time price scheme which is supplied to the customer a day ahead. Many researchers have been working on these concepts, applying different approaches, namely materialistics like genetic algorithms, but also stochastic programming and mixed integer linear and mixed integer nonlinear programming. Our approach was to use mixed integer nonlinear programming, using an index to assess the discomfort to the user alongside the energy cost to be minimized. The model uses the real-time prices for the day, the expected schedule of appliances, and the PV forecast to decide when to charge and discharge and when to operate the appliances. We assume the grid to be a last resort supplier and to be a non-rewarding recipient of the self-generated energy, thus assuming a self-consumption of the locally generated energy. Without getting here into much details, the mixed integer nonlinear programming model considers the inconvenience costs, which are to be minimized, computed as based on an index which uses the square of the difference between the intended scheduled and the effective schedule of the appliances, multiplied by the energy prices and an acceptance factor, which is used to moderate the importance of the discomfort cost in the analysis. The other equations are pretty much straightforward, but we include the computation of the photovoltaic generated energy based on the solar radiation and computation of the state of charge of the battery based on the previous conditions, and which is limited to avoid the loss of the battery life, so the battery degradation. The analysis of results was focused on the amount of expected savings according to different scenarios and on the participation of the battery system in the process. It also focuses the possible disparity between expected and real savings, namely due to the differences between the forecast and the actual PV generation, which is estimated, of course, based on the difference between two consecutive days of the radiation forecast, as well as the sensitivity of results to the variation of different factors, namely the accepted inconvenience. The case study was defined with data sets for different parameters, namely the PV generation data obtained from the photovoltaic geographical information system of the UJRC, the wholesale market prices of the Iberian market operator, the renewable generation data from the Portuguese system operator, and appliances load profiles and load demands, mostly from public databases. The load management was simplified, assuming only two types of shiftable loads, those which can be interrupted, although assuming that the cycle of operation has to be completed, and those which can be shifted but not interrupted. Two data sets of real-time prices were created to reflect what could be a residential real-time price scheme in Portugal. One assumed the current generation mix by rescaling the wholesale market prices, and the other tried to reflect a renewable-only scenario using the inverse of the current renewable energy generation in the Portuguese system to represent the possible fluctuations of such prices, also scaled to the average, to the current average price to residential customers according to Eurostat. From those data sets built with hourly data for the entire year of 2019, we chose extreme cases of days with flatter and more extreme price profiles for different months, aiming to reflect different seasons of the year. The figures in this slide illustrate the cases with more variation in prices for the two types of real-time price. Above is the real-time price based on the wholesale market, which still has significant variations, but not so big as the prices based on the renewable energy sources availability. In this later case, there is a specific day, a single day with a very large variation, which we can consider not to be totally unexpected if we think on loss of the solar radiation in the end of the day, in a situation where the wind and the rain and the water is not there to help complement the supply. The model operated very well and adequately scheduled the appliances and the battery management as needed. The figure in the right here shows a result for a case in January for the renewable energy based real-time price, in which we can see that the grid only supplied in the lowest price hours during the evening to charge the battery and probably the EV battery also. And then the battery and the photovoltaic panel supply the remaining appliances throughout the day. From the 32 data cases that resulted from the choice of the extreme days in 4 months with and without PV and for the two types of real-time price, a significant number produced large savings with a maximum of 88% of the energy costs. The cases in which significant savings were not obtained were the ones without the PV panel for the current wholesale market situation, so for the current energy mix. The battery contributed largely to obtain the load flexibility. In terms of conclusions, we can realize and we can verify that the daily significant variations and deep seasonal variations of the renewable energy sources create a significant variability of the supply, which added to the natural variability of the demand, increased the complexity of finding the essential balance. The present work was able to implement an effective optimization procedure based on day-ahead forecasts of real-time price and solar generation to schedule appliances and battery management actions for a residential customer. Although not intending to make general conclusions by a simple case, anyway, the following can be observed. The current wholesale market variation would not justify a system like this without a PV panel at least. But the renewable energy based power system would probably have significant price variations, and this could lead to significant cost savings with such a system, even without photovoltaic panels, even without self-generation. In detail, to obtain an interesting quantity of savings sufficient to be advantageous against inconvenience cost, a significant magnitude of price difference or a high quantity of solar energy production are needed. With a small PV production, when the price profile becomes more variable during the day due to the relative higher and lower maximum and minimum peaks, the expected savings also increase significantly, only implying a small level of discomfort. The renewable energy-based real-time prices show the true relevance of demand response and energy storage, producing meaningful savings even without self-generation. And this case represents the objectives for this type of home energy management systems as a way to create flexibility to cope with the higher variation of supply costs following the scarcity or abundance of supply. The optimization model was able to respond adequately to a significant price variation resulting from significant change in renewable energy source availability, with an adequate scheduling of the battery, avoiding a significant cost hike. In terms of future directions of work, we will need to include thermal models for some appliances, for instance, water heaters or space heating, to better reflect the role of thermal inertia. The dynamic model of the electric vehicles is also important in order to increase the usefulness of the batteries of the electric vehicles as part of the house storage and flexibility sources. And also the improvement of the control of charging and discharging cycles in order to minimize battery degradation. Thank you for your attention.
Yes, and thank you, Luis, for this presentation. We have one question. First of all, thanks for the interesting presentation. And then the question, how much % of the energy consumption could be shifted using demand response and storage?
So as I showed, obviously that will depend on the circumstances, but in the studied case, we reached circa 30% only with demand response in one of the most obviously interesting cases, but with a less variability of the costs. The demand response part was not so relevant, but the battery storage could reach and reached 80% in some cases. 80% of the energy consumption shifted, but obviously that's that case with particularities with the size of the battery and the size of the house. So it will depend on the analyzed case. It will depend on the case itself. Okay, the objective of Luca's work was essentially the optimization model and to make it work, so it works and it's effective. A complete analysis of the usefulness of it will require a large set of homes and a large set of situations, and of course the specific signals of price that it will respond to in order to assess the real usefulness of the system.
Thank you very much for the clarifications. And myself, I'm positioned in the demand side management education because I'm in buildings, but I'm from a country where there is a supply side management cult, I would say. And this approach, it's quite interesting because it's about how to adapt the demand to the supply. And if we add the cost and the economic feature here, it's getting more complex. And it's really, really interesting to see this approach, especially when we are speaking about the building readiness for the intelligent solutions. Yeah.
But it's becoming more and more important. At least if we look at the plans, the government plans, the European plans for the energy transition, and in the Portuguese case, they are already at least set, and they intend to change the power system dramatically. So expectedly, at least according to the plans, in 2050, 50% of the capacity will be solar. So it's the system is expected to be 100% renewable based. And the change, and we can look at the historical records, because Portugal has already a significant share of wind and already some visible share of solar generation. So we can look at what was the generation profiles, the hourly generation of the past years, and we can see that they change a lot, and they are not being really managed, because the wind and solar are basically they put everything they get into the grid at any time of the year. So basically, when we look at the past profiles, we can assess the availability of those resources, and they change a lot. So if we are going to have a 100% renewable power system, we will have hours in which we will have difficulties, and those hours are starting to appear. There's a case in last December in which the Portuguese system operator had to pay for 1 or 2 hours a huge price, because there was no available resources, there was no available in the interconnections to Spain and to were limited. So the price to supply those hours were huge. So it was a very large overcost. And obviously in such cases, it will be helpful to have solutions like demand response, and to cope, because it's fast, it's much faster than to start anything else. And so this kind of flexibility supply will be much more needed in the near future than it has been. And so we need to find solutions for it. And even part of the plan and part of those 50% of solar energy that is forecast will be by residential customers and individual customers with their own PV panels. And so the management of those of that generation, the use of storage, and the ability to have this kind of flexible management is of utmost importance, in my opinion.
Indeed. We have another question. When do you expect such energy management system will be commercially available, and what may be the investment cost for a home?
There are already some companies at least promising such kind of systems. I do not see those systems as too demanding to be difficult to put into in an acceptable cost for customers. So I think it's not difficult to imagine that in a few years they will be available with higher and higher capacities, because it's not so hard to put these kind of systems into a small box with a smart meter abilities or something. It's feasible, so it's not a difficult product to put into the market. It's more a question of having the need. So it's more a question of developing the market to have, for instance, real-time prices, which now face obviously difficulties due to the market liberalization, and so it's more a matter of creating the market and to creating the system to induce the usefulness of this kind of systems than the product itself.
For the other speakers, do you have any questions, additional questions for Luis? Well, if not, thank you very much for the clarifications and for the discussion. And the next presentation will be on building holistic approach, trying to answer a very big question: how far can building energy efficiency bring us towards climate neutrality?
Hello everyone, myself Shauran Chatterjee. I'm from Central European University. So today I will be showing our modeling exercise where we are trying to find out that how far the building sector can actually push us towards climate neutrality. So as we know that building sector overall responsible for around 40% of the process related GHG emission globally, and therefore it plays a pivotal role to reduce over a global energy demand in order to achieve the 1.5-degree target. And that is why it is really important for us to understand how we can reduce the energy demand of the building sector. In order to do that, at CEU we have developed a model called high efficiency building model. So with this high efficiency building model, we are trying to see in future what would be the total energy demand of the building sector by using different modeling scenarios. Now, high efficiency building model or HEB model considers building as a complete system rather than the sum of components. That means that HEB model considers building as a performance-based approach, but rather than component-based approach. Furthermore, another USP of HEB model is that it considers the state-of-art building energy performances. State-of-art building performances such as passive house standard or net zero standard, which incorporates a very high efficient energy performances of the buildings. And that is why this HEV model is, very unique compared to the other building models we have in especially calculating energy demand for the building sector. So as I mentioned that we have different scenarios in HEV model to calculate the total energy demand. Precisely, we have 4 scenarios defined. First is nearly net zero scenario. So in this scenario, the model in this scenario, what we are trying to understand is the potentiality of deploying net zero energy buildings. Net zero energy buildings means buildings that can produce as much energy locally through the utilization of renewables. Here renewables is the integrated building energy production renewables as they consume on the annual basis. Next scenario, second scenario we have is called deep efficiency scenario, which demonstrates the potential of state-of-art construction and retrofit technologies that can reduce energy consumption at a significant proportion. Third scenario, we have moderate efficiency scenario, which incorporates the present policy initiative. For example, in EU, we incorporate the EPBD guidelines and codes, and for other regions, it's the new building construction codes and policies which are taken into corporation. Fourth and last scenario we have is frozen efficiency scenario. This scenario assumes the energy performance of the new and retrofit buildings, they do not improve as much as compared to the other scenarios because of lower compliances with the building codes. And therefore, we would like to see that in such case, what would be the future energy consumption of the building sector? However, I must reiterate that the purpose of these four scenarios are not to predict the future, but rather to give an insight of what if consequences of certain policies. Now, with these four different scenarios, we have different layers of classification within HEV model. So in terms of geographical coverage, we have 41 regions total, which actually covers the whole world. Second, within this region, we have 17 different climatic regions. Third, again, in terms of location, so where the building is actually located, whether it is located in the urban or rural sector, we have that classification as well. Fourth classification we have is about building categories, that what type of building is this, whether it is a residential or commercial and public. And also third category of building we have is called slum, or in literature it is often referred as informal settlement. Among within this building categories also, there are different types of buildings such as, educational, hotel and restaurant, hospitals, other retail, offices. These are the 6 categories which belongs to the commercial and public building. Whereas in residential building, further disaggregated into 2 categories, that is single family and multifamily, and slum is, itself a category. And now among these different building categories, we have also, as per their energy performances, we have classified these buildings into 5 distinguished building vintage types. That is standard buildings or existing buildings, new buildings, retrofitted buildings, advanced new buildings, and advanced retrofitted buildings. These advanced new and advanced retrofitted buildings are the state-of-the-art performance buildings. Now, let me give you a brief glimpse about the regions we cover. So you can see that this covers almost the whole world. That means that for each of this region, you can see in this map that we are actually calculating energy demand for each of this region. Here, we have 4 focus countries and 12 regions. So among these 4 focus countries or regions, I must say, not countries. So 4 focus regions, we have India, China, USA, and EU27. Within EU27, we calculate energy demand for each of the 27 member states. So these are basically our, geographical coverage of HEV model. Now, in terms of climate coverages, so as I mentioned, we have 17 climate regions or climate zones, you must mention. And this climate zones are defined based on 4 variables. First is heating degree days, cooling degree days, relative humidity, and average temperature of the warmest month. So based on these 4 variables, we have classified 17 climate zones for each of the region. Now, what I should definitely mention here is that this 17 regions, we are reclassifying it as per some new available data. So this classification may change in future. So just a small anecdote. So with this different level of classification, coverages, and building vintages, so the output HEV model produce are basically 2 key output. First is the floor area, second is total energy consumption, and also we produce total CO2 emission. But I must mention that it is, although we can calculate CO2 emission, but we are still updating this CO2 module at this moment. But for floor area and total energy consumption, we do calculate for each of the region, and at a very aggregate level, we do calculate these 2 particular modules. So the results of HEV model. Here you can see on my left hand side is basically the global figure by region, and on my right hand side you can see that by different building categories and their location, the data is presented. So with this modeling exercise, we can see that by 2060 the floor area growth would increase substantially, precisely to be by 77% increase can be observed by 2060. And among this, 77% increase can be observed by 2060. And among this increase, what we need to understand that most of this increase is taking place in the urban regions. And here you can see that this overall floor area growth drivers are mostly taking place in urban area. That is 94% growth is projected in the urban sector. Among floor area growth, what another point I should definitely mention is that this again, the growth of the floor area is mostly driven by three regions. One is Middle East and African region, second is Pacific Asia, and third is African region. So these are the three key regions which observe a significant amount of floor area growth. That doesn't mean that other areas are not growing, but these three areas, in these three areas, we can observe a significant amount of floor area growth. There is another component attached to it, that is the slum, slum area growth, or in other words, that is the floor area growth in the slum population or slum areas. And there we can see that it is a significant growth in the slum area. But when we calculate the total energy demand, some contributes very marginally. And therefore, we actually see that although there can be seen an immense increase in the floor area growth in the slums, the total impact of it are negligible in terms of energy demand. Now moving on to the final energy use for space heating and cooling. Here again you can see that we on my left hand side, the data we have presented here are for world, China, India, U27, specific OECD and USA. So our four focus areas along with specific OECD data we are presenting here. That doesn't mean that we haven't calculated data for other regions. We did, but this is just to respect the time limit. We are just presenting the key highlights from these 6 key areas. So here we can see that in the developed regions such as USA, specific OECD, U27, it is possible to achieve net zero status by 2060 in the net zero scenario. That means that these regions can actually achieve net zero status in the future. Whereas we must also see that China, India cannot achieve net zero status by 2060. And therefore, the world level globally also, the net zero status is not possible to achieve. Globally, the commercial and public buildings in the urban area are the largest consumer of space heating and cooling. And they can actually reduce 33% of total final energy for space heating and cooling by 2060 under deep efficiency scenario. This is the world figure I'm telling you. And residential sector, on the other hand, can reduce up to 57% of its energy under deep efficiency scenario by 2060. So you can understand that energy demand reduction, it can be significant under deep efficiency scenario. Now moving on to the next parameter, that is hot water energy consumption. So similar to the space heating and cooling, hot water related energy demand also presented for the same 6 regions. And here also you can see that the developed countries can actually, developed regions can actually achieve the net zero status, whereas the India, China, and henceforth world cannot achieve the net zero status by 2060. However, as I mentioned repeatedly in the last slide, that although these regions are not being able to achieve the net zero status, but they are reducing significant amount of energy demand due to water heating related energy consumption. So this is really crucial to understand their potentiality. And let us just see then what will happen in the total energy consumption case. Total energy consumption is basically the summation of space heating and cooling and water heating. And here also you can see the similar trends can be seen where developed nations are reaching to net zero status by 2060, whereas country like India, China, and henceforth the world is not being able to achieve climate neutrality by 2060. But here the trick is that you can see here in the bar chart that both India, China, although are not being able to achieve net zero status, but they are reducing a significant amount of energy demand by applying to the high efficiency standard for the building sector. So both for India and China, the deep efficiency scenario and the net zero scenario can actually result a significant amount of reduction in energy demand. But if they chose with with the existing policies to continue in the future as well, then you can see that in both of the regions, the energy demand would go up significantly in the future. And that is why it is really important for us to understand that, uh, you know, uh, we should, no matter what, we should go for a high efficiency standard. And hence, these are the four key conclusions which we would like to draw from our modeling exercise. That is, in order to limit global temperature rise within 1.5 degree, building sector plays a pivotal role. Both deep efficiency and net zero scenarios suggest to have a stringent building code efficiency for all across all the regions. And let me break it down that for the developed nations, particularly, it would be important to renovate the historical buildings, advanced retrofit the historical buildings, and for developing regions, it is really important for the new building stocks to adhere to a stringent building code that requires a high level of energy performance for the new construction. So saying that, I would like to say thank you for your attention, and I would like to hear if you have any questions. Thanks.
Thank you, Suran. I have a question.
Before you take that question, I would like to have a short dialogue with the regarding the presentation.
Yes, please do.
Because I think it was very good, and thank you very much for the material. It really point out the need for action now, and what I'm also seeing is that we are moving to 2025, 2030 before things are starting being reduced. At least when I look at your presentation. So we have to start now for sure, and it's very interesting to see. I have maybe two questions. You mentioned CO2 in the that you had included CO2 in the evaluation, but you didn't present anything on that. Can you elaborate a little bit on that as well? And then finally, when you look at CO2, do you look at the overall performance of the building throughout the building lifetime? That means also embedded energy and recycling, or do you only look at CO2 only in brackets, of course? Do you only look at CO2 in the use phase?
First of all, thank you so much, Gert, for encouraging comments and your appreciation. So as I mentioned during my presentation, that we are, still improving the CO2 module, because the reason you just mentioned that we also want to incorporate the life cycle of the building into while calculating CO2. That's number one. Number two is when we talk about CO2, it is often the case that we calculate only CO2 emission. But here we need to understand that there are a lot of materials involved in building construction, and hence probably it is recommended to calculate the GHG emission instead of CO2 emission. And that is why, we are right now debating and updating our module to incorporate all these comments and changes so that we can present a significant figure which can be useful to show that what we are missing out or what we can achieve actually. So I guess I have combined both of your questions here.
Yes, you have. And then one recommendation. Sure. We will have the climate conference in Scotland in November. Your presentation seems to be very interesting there as well. So should you have any option to go there, please take that into consideration. It would be a tremendously good discussion to have there.
Sure. I would love to know more about it. Thank you so much. We can get in touch later.
So we have a question, and this is related to a question that I wanted to make. Do you think it is possible to attain deep scenario? And if so, where would be this possible? This is from Heidi.
Okay, I mean, deep scenario, whether it is possible, I mean, of course, it is possible, feasible, and but what we wanted to see with our modeling exercise is that, what will happen if we go with efficiency standard? For example, in deep efficiency scenario, we assume that all the existing building codes, if we implement and adhere and also have passive house standard buildings at a certain proportion, then what will happen in future? And with that, we could see that, it is actually giving us a significant reduction. And therefore, we need to see now that what are the changes, like researches from Heidi's and Louis, we can see that how we can adhere and implement all those technologies, new technologies, to achieve that level of demand reduction. So this is how I see our research actually.
Okay, and why is there such a difference between the moderate scenario in the United States and the one for EU 28, now 27? And I also remarked that for the European scenario, there is no such, not a big difference between the moderate and the net zero scenario. Moderate and deep, sorry.
So you are in a way right, because existing so as I mentioned that we have taken into existing, building policies and building codes of the EU, and existing building EU codes and policies are already at an improved state, but we need to see that how much it can be further improved in order to achieve our climate neutrality. And that is why, you can see that there is still a difference, but not as huge as, compared to other regions. Whereas in case of USA also, we have taken some US related building codes. And before we incorporate this level of input data, we have talked to several building developers from US as well to understand whether, what type of data available. And apart from that, to understand that whether it is actually the case, what is actually documented in the official documents, because we always make sure to take the official reported data as to use as our input data. And in order to compare between EU and US, I think these two are kind of different context, because it has much more, I would say, in terms of, if I just only see the data, it has a lot of layers, especially in EU, the different member states and all those, whereas in US, we are taking just the national figures. But I'm sure at the state level, they have different building codes and all those issues. But our objective here was actually to capture the national one. Hence, we had to discard the diversity and just take the national report figure. So I assume that, the difference probably are coming from that, but the direct comparison between EU 27 and US probably would not be very, let's say, we are not at that stage to directly compare between these two regions, but rather to see their energy demand production reduction potential.
Okay, and coming back to the discussion earlier, this would come with another question from Heidi. Do we have to conclude that 2060 carbon neutrality target is not achievable for the building sector?
So for the building sector, if you talk about world level, then yes, that is what our data is showing. And the reason behind is mostly, developing regions such as India, then specific Asia. So these regions are actually, it is not possible in this region to achieve climate neutrality by that time, that is 2060. And that is why at the world level also, it is not possible to achieve, because world is just a summation of these regions, right? So that's, unfortunately, that's the case. But again, we never know if some drastic improvement, some huge policies are taken into these regions, then it is possible. Why I'm saying this? Because so far with our, the input data we have, we could see that both in India or China, there are not much share of advanced retrofitted buildings or advanced building per se. China is still doing better than India, but these two countries share a highest floor area growth as well. So that's why if these two countries fails, then globally also it would be difficult to achieve climate neutrality by 2060.
Okay. And coming back to the CO2 that was included in the model but not presented, maybe it's a silly question, but it's in the context of polemics that we are having now in Romania in the modification of the technical regulation for calculation of energy performance of buildings. How do you calculate in this model the CO2 emissions based on final energy at the building level or based on primary energy?
So we calculate based on final energy, but as I mentioned that we don't want to only calculate CO2 emission, but rather we are approaching towards calculating a GHG emission. If we do that, then we also incorporate, the building life cycle, as well as we also need to see whether we calculate the embodied carbon and cradle to grate approach to calculate the total life cycle GHG emission. But there are severe, methodological debates we are having. And that's why the present module we have is just to, calculate CO2 emission. So we thought that we should go beyond that. And that is why we didn't present it, that we are still on the stage of development.
Okay. It would have been a nice debate on that, but not in the limited time of the sessions. Yeah.
I have one comment again, and it is that the presentation also shows very clearly that between now and 2060 we have to build as much square meters as we are using today, or almost as much square meters as we are using today. So the challenge is not only to make the existing building stock energy efficient. It is of course a big challenge, and we shall meet that. But it's also to look at all the new buildings that are coming up, and we have to reduce to zero, even though that we double the amount of square meters. It's really a challenge that we have in the construction sector.
True.
Yeah.
I mean, I just would like to add one point to your comment, and this is absolutely true, and I agree with you. During our modeling exercise, we could understand that we model from 2022 to 2060, and during this period, there will be a lot of floor area which needs to be either renovation or new construction would take place. And if we do not, take into account all this, then we probably total energy consumption would go up, as you can see in our data as well. So that is something we really need to take seriously now.
Agree.
So the conclusions imply that if developed countries contribute to deep renovation in developing countries, the world could achieve zero energy by 2060. Do you agree? It was a question from the attendees.
Yes. So if this, India, China, especially, these to have a largest floor area in terms of country, they can actually implement a far more ambitious building stocks and added to a strong stringent building energy performance code, then probably in future it is possible to achieve climate neutrality status by 2060. But at this moment, these regions are not in that state to achieve net zero status by 2060. And it also depends on their economic status and population growth, GDP. So we need to take into consideration all this. So if we do that at this point, even with net zero scenario, it is not possible.
Yeah, it's a good point. So thank you very much for this discussion. And I think it was more relaxed for the session because we had only 3 presentations, but we are slowly going to the end of this session. And I will just want to make two announcements. The first one is related to our panel. So the panel 8 buildings will have the next session. So we will meet you in half an hour. It will be a parallel discussion with the topic new gym consumers to create good indoor comfort at low use of energy. And the second one is also for today. There will be two informal sessions later in the afternoon. One will be led by Paolo Bertoldi from the European Commission. It will look at the impact of energy efficiency projects on property values, rents, and credit risk. And the second one will be led by Cédric Jeanneret from SIG. We'll discuss a concept for a pan-European interactive knowledge transfer platform for radical energy savings. Both sessions will take place at 4:15 Central European Time and will be on Zoom meetings mode, so you can join fully in the discussion. So thank you very much for the fine lineup of speakers that we had here and for the interesting discussions. And I'm looking forward to welcome you in the next session of this panel.
Thank you.
Thank you. Bye.
Bye bye.